Okay, so hi, this is Ali again, and I want to continue talking about the uh, like some feature selection mechanism that we did in our example. So after we've done pre-processing, if you remember from the other video, um, here we're going to perform some feature selection. So all these pre-processing steps enable us to know what are the different variables that we have. And for example, here we took a look at this um, like plot here, and it seemed like that the competitor rate versus our rate could be competitor rate could be some indicator of whether the applications are going to be funded or not, because um, like most of the time it seems like our rate has been uh, a little bit higher than the rate of the competitors, and that could be the reason that we didn't some of these applications didn't get funded. So um, what we want to do right now is we want to create like some feature, choose some of the features from the feature list. So here we have chosen the rate, competitor rate, the amount, and the risk score. So you could choose the amount or maybe the log of the amount, but these are what we try to use. Uh, so when you use these four features, then you create that list. And here the input, the x of the input of my kind of model is the mortgage and only the columns that I have selected. And the y, the output of my model is going to be the funded flag. So funded is 1 if that application was funded and 0 if it's not. So I put funded into the y and all these four features into the x. That's the features that I have chosen. And now I want to split the data into like training and testing data. So scikit-learn is going to provide us with some tool to do that. You could just simply do that by using pandas or numpy, which is not very difficult. Or you could use some of the libraries that are available for you. So the train and test split is going to this functionality of this scikit-learn is going to get the x, which is your input, and the output. And it also gets a random state because it randomly selects these variables for you, and it does it in a from a, like a it does a stratified sampling. So to make sure that what you get is what you like what you need. So basically, this random state allows you to repeat this scenario. So if every time that you select like do some randomization, you do just randomly, then it's very hard to repeat a process and to find errors or ask other people to like repeat your process. So by choosing a certain random state, you could put 0, 1, or any other number. Every time that this train and test split is working, it generates the same X train, X test, Y train, and Y test. So these sets here are like you train test split receives the two data, like the two matrices here, which is the X and Y, and it splits them by default by 80-20. So 80% of your input will be put into X train, and 20% of that will be put on will be included in the X test. So this is going to be the training data that you use to train your model, and this is going to be the test data that your model does not see until the testing like section of your code. So the Y train is the labels. If you have any labels, that's the labels, and this is the label of that 80% data. and this is going to be the testing labels. So these two, like y-train and x-train, will be given to your model to actually to help it train, and x-test will be also given to your model after the training is completed to receive the results, but the y-test is never given to your model, and it's going to be compared with the results that your model is given at the test time. What we have here is also some normalization. So min-max scaler, what it does is that it helps us create a scaling system on your data. So so right now, like the different inputs, the x and like we just apply to the like input of your model. So we apply it on x. So we create what we do here is that we create a transformation on the x only, like the train data. You cannot by default because you haven't seen the output data, like the test data. It's better to put it's more realistic to create a transformation on the train data. So what it does is that it tries to make all the values between 0 and 1 or -1 to 1. It just makes it normalized, and it finds the maximum value and the minimum value and just make sure that all the data are normalizing to like a certain amount, 0 and 1, or maybe -1 and 1. And you could just change the option to do something otherwise. The same here, like train test split, you could just add some more options and like give it a different ratio. So X-train and X-test is now ready now with the same transformation that we applied on the training data. We applied that to the test data as well. So now if you take a look at the like if you want to see what is the training data looks like before actually the transformation looks like this. These are the 4 variables that we have, and also this is the flags like funded or not funded. So these 4 here are not funded. This certain one is actually funded, and you can see here that our rate was lower than the competitor rate. That could be a very like some indicative whether this application was funded or not. Now that we created our data and the features here, we can use scikit-learn and input some of the libraries that is available there. So decision tree classifier is one library, but logistic regression is also there. K-nearest neighbor is also there. So you could import one of these, any of these, and now you call the fit function on that classifier. So fit basically trains your classifier, and fit the supervised data. So this is a supervised learning environment, and I fit the x of train and y of train to that model, and now it creates a tree for me here, and that tree I can basically try to see how well it was trained. So once this training is completed, I can call a score. A score basically tries to see how fit your model is. So we can try it with 2 different scores because we have 2 sets, once on training and set and once on test set. We do that so that we know whether this model is overtrained or not. If it is overtrained, like this example here, it seems like it is been overtrained because the accuracy on the training set is actually 100%, and the accuracy on the test, when we just tested on the X test and YF test, is 86%. So it's a little bit overtrained. So if you try logistic regression, you can see that, well, it's like again, we call the fit function there, it gives us to 85% training and testing. Is kind of more balanced classifier. The near neighbors is a lazy classifier. So it's basically when you say fit this X and Y, it kind of stores all that data and just searches all the data to try to find the first K neighbors. By default, I think K is 3 or 5 if you don't put any values here. And here you could see that it didn't perform 100% on the training set, but it performed 88%, which is higher than any other classifiers that we have. So sometimes even simple classifiers perform well. It depends on your data. So once you've done that, it's very important to not to stop right there and go ahead and try to get other metrics. So one very important tool and some important metrics that you could get are achieved by using the scikit-learn metrics library and classification reports and confusion matrix. So first, when you if you have a prediction, you could just say knn.predict and give it the X of test. It gives you the prediction that knn actually provides. And this classification report that is provided by scikit-learn, it receives the true values, which is Y of test, and the estimates or prediction that is given by your model. And it receives these two values and creates a classification report. So this was for the KNN. So you could see that in this case, the precision and recall are the same, like 88%. But there are the recall or precision is different on maybe each class. So for not funded class, the precision is 91 and recall is 93. It's less for the funded class. So it's easier to know which ones are not funded. It's more accurate, but we're not that accurate compared with the other class to know which ones are funded. So so that's not bad. It means that we can reject a lot of applications that are not going to be funded quite easily, and then give the rest to maybe a human operator. And the support here means that how many examples that we had. We had around 20,000 not funded, and here 9,000, 8,500 funded. The total that we have here is 28. We had over 100,000 samples, but only 28,000 unseen samples. Around 20% of the total data is given to your model. That's why that's the total amount. So here you could actually try to test your model for unseen data. So because the data is your model expects transform data, so I say knn predict this one sample, which is 0.5, 10%, I don't know, 0.5. This is representative of these competitor rate, amount, and risk score. I put it between 0 and 5 because the data is actually now normalized using the min max scaler. And yeah, you could take a look at the data, run it, and see that if you print the actual X and Y, you will see that. So now if I print the predicted amount, I'll see that it shows me 0, which is not funded. And I could go, this is a test case, and I could go and take a look at find this specific value maybe in the mortgage and see if that specific one was actually funded or not, and that was not funded as well. So we had a specific case like that. And here, like this is a code that's maybe sometimes you could use, and this shows the distribution of whether the Canaan, I think this is, let me see whether it's from Canaan or not. Yeah, we have some, this is a prediction from the decision tree. Yeah. So using this decision tree, let me plot. Yeah, it's actually, okay, I set CNN here. Yeah, it's, okay. Yeah, I changed it. It's actually Canaan, and then, yeah, CLF is just the classifier. So CLF is a classifier, the Canaan classifier. So this is the Canaan classifier that I have with K of 3. And you could see that this is a distribution of both classes, and whether based on the competitor rate and the actual rate, it shows which of them were not funded and were funded. So if it was, the rate was around maybe I don't know, 4, and the competitor rate was 8 or 10 or 12, they were all funded. So you could see all this distribution, and any rate around maybe over 5, any rate that we've provided were not funded. And that may basically mean that there has been some other factors that are not here. Maybe if we give someone a very high rate, it's because their credit score is so bad, and that's why it's not funded. Because you can see we have 8 here, and also although the competitor rate could be higher than that, 8, 9, 10, 12, the application was not funded. So and this is the for the Canaan, this is the algorithm that like it's a simple algorithm that helps you find the maybe an optimal K. So what it does, it basically, because right now our data set is not very big, it goes over all the different ranges of K from 1 to 20, and for each of those creates a different classifier, and it adds number of neighbors, and underlying neighbors gives the actual K, and then it trains it and it scores it. So this is basically what we've done here, is an example of a simple grid search. So if you're looking for hyperparameters, so hyperparameters are parameters of your model that are very high level. So the value of K could be quite meaningful in deciding whether you get a better classifier or not. You can see here, if you choose K of 1, it basically is going to give you a little over 65% accuracy. But when you go over, and maybe it's interesting, like different Ks, even the odd and even numbers of Ks, is going to give you a totally different accuracy. And it merges at some point, maybe K equals 14 or so. But you can, depending on the size of your algorithm, you could just stop somewhere around, I don't know, this is 5, 6, 7, 8, or 9. And yeah, it starts from 1 and it ends at 19. So so this was all, and this is how you could start, maybe try to select your features, do the train and testing, split, normalize your data, and train your classifier, test it, get the classification report and confusion matrix. Confusion matrix is very useful for multi-class classifications. You will need to use that if you don't use a confusion matrix. It's very hard to find and debug your kind of classifier. And you could just take a look at different variables and plot them and see if like there's a meaningful distinction on a certain variable that determines whether a sample is actually belongs to a certain category, outcome category. And don't stop there, and try to do more and try to find the best variables. Now that you've done classification from the start to the end, don't stop there and find the best parameters. Maybe you can get even a better result by changing some hyperparameters. So you could put it in a grid search. A grid search is basically like similar to this, but you may have more than one variable. So just put 2 for loops for each hyper parameters. Sometimes it's possible, sometimes it's not. There are other ways like optimization methods, like you could create another machine learning algorithm to find the best parameters for you. There is genetic algorithm to search for the best parameters, which is also quite interesting. Yeah, that's it. Let me know if you have any questions, and take care.